Hello, Joe Shaw here, full stack engineer in the Incubation engineering department. My focus is application performance management, monitoring and observability as a single engineer group, so we can bring an observability platform into GitLab. This is my weekly update video. Here's the issue I've created to cover that. And I'll link to the recording soon. You can subscribe to the weekly issue links from there. So in the last week, I've been focusing on creating a metric schema for Clickhouse that will be very flexible, that will support any number of measurement of dimensions and store things in a flexible way that is also reasonably performant compared to the existing solution. So if we have a look at that, previously we'd used Clickhouse. We've evaluated Clickhouse to see how that will work with respect to sort of metrics and time series data against things like timescale DB. It performs very well, and I was happy with that evaluation. So we're going ahead with using Clickhouse. So I've been refining a design for it. So in the existing benchmarks with Clickhouse, the schema that I've used for the metrics is very restrictive. So for each measurement, if you will, there's a separate table. So you can see, for example, here there's a CPU table that has these sort of typical fields like a created date, created at, and a time. And then it's got all the CPU fields baked in. Now, the obvious problem with that is, if that CPU measurement changes, or we have a different agent or a different style of collecting metrics, then you have to modify this table and make this table flexible, or have duplicate tables for different styles or different measurements. And it's not really flexible at all. So there'd be a table like this for every single measurement. So it might be disk IO, it might be some kernel specific resources, it might be like pod memory utilization, for example. And then it has, again, a tags table that's very fixed, that has really very specific tags for this benchmark. But again, in reality, you can't have a fixed tags table because you know that your users are going to have arbitrary tags. The only thing we can really condense out of that is the host name, which we know would be in most data sets. So again, this performs very well with the queries, as we'll see, but it is not flexible enough for our use case. So moving on from that, what we do is we start with a naive schema where we basically just denormalize this and flatten it down. So it has the timestamp and host, a measurement, a field and a value, and an array of tags. So every one of these fields in here then becomes an individual record. And it's a naive approach, so we get a baseline of how badly can we do it without putting any effort in. Then we're refining that to create a better solution, we think. So I benchmark that as well. And then looking at the actual refine table, the process we went through, we start looking at codecs that we can use for better compression. So the timestamp is better with this double delta codec, which is really good for sequences like times, ideally ones with like a fixed gap between, which might not always be the case, but it compresses this very well. Low cardinality strings for a lot of the fields. So this uses a different data structure in Clickhouse for strings or any particular compatible cardinality type that doesn't have a large set size. So that's quite ideal for things like the measurement name and maybe certain tags. In reality, it probably wouldn't work for hosts because you would have lots and lots of different named hosts. If you're looking in a real data set, for example, if you've got clusters in Google Cloud, they're going to have loads of unique hosts. So that might not be appropriate, but for this benchmark, we're leaving it as low cardinality. And then for the actual value, we're changing that to a gorilla codec, which is being designed as part of a research paper from Facebook, where they were designing a time series database, and the gorilla codec forms an XOR between adjacent binary values. And so if the values don't change very much, it significantly reduces the space required on disk. Then we put in partitioning. So partitioning by day, so the actual chunks that are being written to disk getting partitioned, and then Clickhouse, when it's looking at queries, can only load and search indexes that are relevant to particular partitions. So that's quite useful. And each one of these changes we benchmarked, and we got gradual better improvements as we went along. And then we actually moved the tags and fields into nested structures. So rather than having a completely denormalized method as in the naive one, we bring it back into having the fields in the same table as the measurement, but having the flexibility that those fields are just sort of key value pairs. And you can see the table structure we end up with there. And this is what we're benchmarking against. And I think this is, you'll be glad to hear, if you've watched my previous videos over the last few weeks, the last benchmark I intend to do for a while. So that's good. So yeah, so we couldn't use the nested structure here for the fields because I couldn't find a way of getting the codec to apply properly in that format. The nested data structure there allows you to specify these nested arrays, and it will validate that the length of them is the same, which is really useful when you're inserting data. So that makes sense. So let's have a look at us benchmarking this against timescale DB. We wanted to make sure we reran that as well, just to verify the previous results and compare it here. I didn't want to use the old benchmarks, just to make sure we got fresh runs. Default Clickhouse design, which is this sort of optimal design that I showed you that wouldn't really work in the real world. Our single table naive solution, which we expect to perform quite badly, and then the single table refined solution, which is this one up here. And I'm using the DevOps data set. So we're not only getting CPU data in there, we're getting, I think there's about 10 different data sources. So when it comes to having a single table there, that table is where all of those data sources are going, as opposed to going into separate tables, which does put a burden on that table in terms of performance. So we have to kind of tune it and make sure it works well. And we're using different scales, so 10 hosts, 100 hosts, and 1,000 hosts. And that's it. By the time you get to 1,000 hosts for the simulated data set, it is quite large. So that should work well. So here we go. So loading metrics rate. You can see while the refined one doesn't perform as well as Clickhouse itself, it performs slightly better than timescale DB, so that's good. Volume sizes pretty small for the refined solution, even smaller than the original Clickhouse one in some cases, so that's great. Now we're getting to queries, and as I go down, you'll see the refined solution performs pretty well. The single table naive solution even beats timescale in certain cases as well, as you can see, like here and here. And there are a few outliers, but it never performs particularly badly. And this is 95th percentile. So again, 95% of all the results in terms of latencies are doing much better than this. So this is kind of almost worst case scenario. So I'll quickly scroll through here. So there are only a few where the single table one, refined one, does relatively badly in comparison. And this one, the timescale DB one, didn't even return properly. But these are, as we get further down here, these are queries that are quite unusual, very high stress queries. and not at all the sort of thing that we would actually be using the data set for. It's just to kind of put it through its paces. So yeah, so still doing quite well in this section. Again, for example, single group by does very well there as well. As you come back down to some of the end ones, again, performs very well. So we can be happy with that. We could, as it gets put into real use, we can then start analyzing the queries that are actually getting run and see if we need to do things like have materialized columns or views on top of the data set. But I think this is fine for the time being, as far as I can tell. So moving on to the actual CPU and memory use, you can see that it has similar profiles to Clickhouse itself in the normal table setup. And as the dataset gets larger, CPU usage is pretty good. And actually, its memory usage over the runs is generally better than all of the cases as well, especially the much larger run down here. It has a very solid memory profile, whereas sort of timescale is really stretching up to well over 60 gig. And Clickhouse as well is using quite a lot of memory. So that's a really good sign. So I'm happy with that. So I'm going to go ahead and then use this schema that we've got all the way up here. I'm going to use this schema going forward with the build of the metric storage, and hopefully that will work well for us and be very flexible. The only other thing I added to the issue here was there are a few links I found while I was designing that. There's an article here about how you design time series efficiently, some information about the codecs that I'm using, some nice feature slides, and there was an article about recently Clickhouse incorporated and it's become its own company as well, which is great to see. Hopefully that means a lot more releases and new features from them, which is fantastic. Okay, that's it for me, and I'll see you next time.